it's possible that you might be asked to find the area of a rather awkward shape. By this, I mean a shape for which our usual integration might succeed, but it's probably a lot of work. When faced with such a problem, a common technique is to attack it from a different direction, perhaps literally. So in this video, we're going to look at how we can integrate a curve in the y direction. You can't see me making air quotes, but I am. Let's start with something that isn't awkward though, just so that we can illustrate what it is that we'll be doing. Let's take the curve y equals x squared on the interval 0, 2. I'll throw up a graph of this quickly so that we can see our areas at work. If we compute the integral of this curve with respect to x, we can apply our usual techniques, arriving at an answer of 8/3. This is our usual area under the graph of f. Let's do this again, but now let's solve our equation as a function of y. This time, we'll integrate on the interval 0 to 4, since that's the range of the y variable. Mathematically, the techniques we use to integrate with respect to y are identical to those of x, and working it all out gives us 16/3. Geometrically, this is the area between the curve and the y-axis. Now, it won't be important to the rest of our discussion, but something cool happened here. If we add these two areas together, we get a total of 8. But look at the red and green areas above. They form a rectangle. And 8 is exactly the area of that rectangle. So I think that's pretty cool. Now I mentioned that we tend to use this when we're given awkward shapes, but y equals x squared isn't very awkward. So here's something that is. Let's find the area bounded by x equals y squared minus 2y minus 3 and the y-axis. Again, it won't be necessary to complete the problem, but I always like to graph these things out. If we set x to be 0, we'll get the y-intercepts, and factoring the equation shows us that the y-intercepts occur at -1 and 3. The x-intercepts occur when y is equal to 0, which we can very quickly evaluate to find x is equal to -3. Finally, I want to find the x minimum, the leftmost endpoint of the x-axis, which we can do by either using calculus or completing the square. With calculus, we'll find the critical point by differentiating, which gives us y is equal to 1. Completing the square gives exactly the same answer, where we find again that the minimum occurs at y equals 1, and that x equals -4 is the leftmost endpoint. So in either case, y equals 1 and x equals -4 is the leftmost endpoint of the function. We have enough information to start putting this all together. We'll mark off the points that we found and connect them with a parabola. This isn't the prettiest graph, but you know what, it's still going to help us see what's happening. So now we integrate our function on the interval -1 to 3. And again, this is because that's what the range of y is. And our integrand is just a polynomial, so this isn't too bad, and we end up with an answer of -32/3. Be sure to confirm with yourself that getting a negative answer here makes sense. From the perspective of x as a function of y, this function is everywhere beneath the y-axis, and so the area should be negative. And as one last thing, I will leave you with a bit of a challenge. See if you can compute the area above by integrating with respect to x. It is doable, but it's a lot more work than integrating with respect to y.